Out there in the vast, silent darkness of space, something impossible is happening. A galaxy spinning in perfect spiral arms where none should exist, defying the laws that govern everything else in the cosmos. This isn't just a cosmic oddity, it's a full-blown rebellion against the rules of the universe, a dance through time that shouldn't be possible. And yet, there it is, shimmering against the black, a puzzle written in starlight. This is the story of the spiral that shouldn't exist, a mystery so profound it's rewriting what we thought we knew about galaxies, time, and the very fabric of reality. Picture this, a galaxy so ancient it should have settled into a calm, shapeless haze by now, its stars scattered like dust. Instead, it's whirling with the grace of a cosmic ballerina, its spiral arms stretching across light years as if time itself forgot to touch it. Astronomers first spotted this celestial rebel and did a double take because, according to everything we've learned, this galaxy should not look like this. Its existence is like finding a perfectly preserved dinosaur walking through a modern city, untouched by the millions of years that should have worn it away. What's keeping this spiral alive? What force is bending the rules of physics to preserve its impossible dance? That's the question we're diving into today. This isn't just about one strange galaxy. It's about the boundaries of our understanding, the moments when the universe looks back at us and winks, reminding us there's so much left to discover. We'll trace the clues scientists are following, from the galaxy's mysterious origins to the mind-bending theories that might explain its defiance. By the time we're done, you'll see the cosmos in a whole new light, where the impossible isn't just a fluke, but a doorway to something even grander. So buckle up, we're about to take a journey into the unknown where the rules are broken and the stars themselves hold secrets we're only beginning to uncover. The year was 2018 when the unthinkable appeared in the data, a flawless spiral galaxy glowing in the distant cosmos, right where theory insisted it couldn't be. Astronomers using the Hubble Space Telescope and the Atacama Large Millimeter Array were mapping the early universe, expecting to find only the faint, chaotic blobs of ancient galaxies still clumping together. But there, nestled in the noise, was a structure so crisp, so undeniably spiral-shaped, it sent shockwaves through the scientific community. The galaxy, catalogued as a 1689 B11, wasn't just defying expectations, it was rewriting the timeline of cosmic evolution. Initial reactions ranged from skepticism to outright disbelief. One researcher joked they'd need to check the telescope lenses for smudges, while others scrambled to rule out imaging errors or gravitational lensing distortions. But the more they analyzed the data, the sharpness of the spiral arms, the precise rotation curve, the clearer it became. This was no glitch. It was a real, fully formed spiral galaxy existing a mere 2.5 billion years after the Big Bang, a time when the universe was still a turbulent nursery of colliding gas and infant stars. What made the discovery so unsettling was the sheer improbability of it all. Spiral galaxies like our Milky Way were thought to be the refined products of cosmic maturity, requiring billions of years of quiet evolution to sculpt their delicate arms. Yet here was one that had somehow achieved perfection in a fraction of that time, amid conditions likened to a stellar hurricane. The implications were staggering. Either our models of galaxy formation were missing a critical piece, or this galaxy had found a way to cheat time itself. The key to the mystery lay in the galaxy's unexpected surroundings. Instead of drifting alone in the void, it was part of a dense galactic cluster, a place where gravitational chaos should have shredded any delicate structure. Yet against all odds, it had not only survived but thrived, its spiral arms intact. Some theorists began to wonder if the very forces that should have destroyed it might have instead acted as a cosmic sculptor, compressing gas and dust into those iconic swirling patterns far earlier than anyone predicted. Others proposed dark matter might be playing a hidden role, stabilizing the galaxy like an invisible scaffold. But the most tantalizing clue came from the galaxy's stars themselves. Spectroscopy revealed populations of ancient stars coexisting with vibrant newborn ones, suggesting a history far more complex than a single, smooth evolution. It was as if this galaxy had lived multiple lives, each phase leaving traces in its spiral arms like rings in a tree trunk. The discovery didn't just challenge textbooks, it hinted at a universe where beauty and order could emerge from chaos far sooner and in far more hostile places than we ever dreamed. Spiral galaxies aren't supposed to survive in bad neighborhoods. Think of them like delicate sandcastles. They form best in quiet, undisturbed places where gas can slowly swirl into those iconic pinwheel arms over billions of years. But this cosmic rebel, this so-called impossible spiral, didn't get the memo. It's thriving in what astronomers call a high redshift protocluster, a chaotic, crowded region of the early universe where galaxies jostle like commuters in a rush-hour subway. Gravitational tides should have ripped its structure apart, while violent collisions with neighboring galaxies ought to have scrambled its stars into a shapeless blob. Yet somehow, against all odds, its spiral arms remain pristine. To grasp just how bizarre this is, let's compare it to the Milky Way's own backstory. Our galaxy grew up in relative solitude, leisurely gathering gas and dust over eons, undisturbed by the kind of cosmic traffic jams the impossible spiral endures daily. Even the famous Whirlpool galaxy, with its textbook-perfect arms, sits in a calmer suburb of the universe. But this renegade, it's like a ballet dancer performing flawlessly in the middle of a mosh pit. The secret might lie in an invisible dance partner, dark matter. Some researchers suggest this galaxy's halo of mysterious dark matter could be unusually dense, acting like a gravitational shield that deflects the chaos around it. Others propose it's feeding on gas filaments, cosmic conveyor belts that funnel fresh material straight into its spiral arms, constantly replenishing what the turbulent environment tries to steal away. There's even a wilder idea that the very turbulence itself might be compressing gas clouds into new stars at just the right rate to maintain the spiral structure, like a juggler adding balls to the pattern faster than they can fall. Then there's the timing problem. Spiral arms are notoriously high maintenance. They're not static sculptures but dynamic patterns that need constant renewal. In most galaxies, they're thought to dissolve and reform over time, like waves cresting and breaking on a shore. But the impossible spiral's arms appear strangely persistent, as if someone hit pause on their natural decay. Could it be locked in some kind of gravitational resonance with its violent surroundings, a delicate balance where external forces somehow stabilize rather than disrupt? Every answer seems to lead to deeper questions. For instance, the galaxy's core hides another puzzle. Its central black hole isn't just unusually quiet, it's practically asleep. In such a chaotic environment, we'd expect it to be gorging on gas, lighting up as a brilliant quasar. Instead, it's dormant, as if the galaxy found a way to starve its own monster while still feeding its spiral arms. This defiance of expectations isn't just a fluke. It's a challenge to our entire understanding of how galaxies live, die, and dance through time. And that's what makes this cosmic outlier so thrilling. It's not just breaking the rules, it's showing us the rules might be far more flexible than we ever imagined. Dark matter may be the universe's best-kept secret, an invisible force shaping galaxies from the shadows, and this impossible spiral could be its masterpiece. Picture a cosmic puppeteer, its strings made of gravity, gently holding the galaxy's delicate arms in place against the shoving match of its chaotic environment. That's the role some scientists believe dark matter plays here. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light. It's detectable only through its gravitational pull. And in this galaxy's case, that pull might be the reason its spiral structure hasn't been torn to shreds. The theory hinges on something called a dark matter halo, a vast, invisible cocoon enveloping galaxies like ours. Normally, these halos act as stabilizers, their gravity keeping stars and gas from flying off into the void. But for the impossible spiral, the halo might be doing extra duty. Simulations suggest its dark matter could be unusually concentrated, creating a gravitational buffer that deflects incoming chaos from nearby galaxies. Think of it like a force field, absorbing the blows of cosmic collisions while the spiral inside remains unscathed. Not everyone's convinced, though. Some astrophysicists argue that dark matter alone can't explain the spiral's pristine arms. They point to galaxies in similar environments where dark matter halos exist, yet no spirals survive. This has led to a fascinating debate. Could there be a sweet spot in the balance between dark matter and ordinary matter? Too little dark matter, and the galaxy gets shredded. Too much, and the spiral might never form at all. The impossible spiral might be threading that needle perfectly, its dark matter halo tuned like a finely calibrated instrument. Then there's the timing puzzle. Dark matter halos take time to build, yet this galaxy's spiral appeared shockingly early in cosmic history. One radical idea suggests its dark matter could be primordial, formed in the first moments after the Big Bang, giving it a head start on shaping the galaxy. Others propose that the surrounding cluster's collective gravity somehow funneled dark matter into place faster than usual, like a cosmic shortcut. The most tantalizing clue comes from the galaxy's rotation. Spiral arms rely on a delicate dance between gravity and motion, and this one spins with eerie precision. Some researchers think its dark matter isn't just a static halo but arranged in a specific dynamic pattern. Perhaps a lopsided or warped distribution that reinforces the spiral's structure. Imagine a potter's wheel with an uneven weight. The wobble could create unexpected stability. Of course, dark matter remains maddeningly elusive. We've never directly observed it, and its properties are still theoretical. That's what makes this galaxy so invaluable. It's a natural experiment, testing our ideas in ways no lab ever could. Whether dark matter is the sole architect or just one player in a larger cosmic ballet, the impossible spiral is forcing us to rethink what we know about the hidden scaffolding of the universe. And with every new observation, the mystery deepens, reminding us that the cosmos still holds cards it hasn't shown us yet. Time moves differently in the cosmos. While Earth's mountains rise and crumble over millions of years, galaxies typically transform on scales so vast they make human history look like a blink. Yet this impossible spiral defies even that cosmic clock. It's a snapshot of the early universe, preserved with eerie perfection, as if someone pressed pause on its evolution. Normally, spiral arms are fleeting things, their delicate structures vulnerable to the gravitational tug of war of nearby galaxies or the slow erosion of internal forces. But this one, it stayed crisp and defined for billions of years, like a fossil trapped in amber while the universe aged around it. The mystery deepens when we consider what should have happened to it. Galaxies in dense clusters are like cars in a demolition derby. Constant near misses and collisions leave them misshapen, their stars scattered. Yet this spiral's arms are untouched, its symmetry flawless. One theory suggests it might be a cosmic fugitive, ejected from its chaotic birthplace early on and left to drift in relative isolation. But the data tells a different story. It's still very much part of the cluster, dancing through the chaos without a scratch. This is where the idea of a time capsule galaxy gets even stranger. Most relics from the early universe are either tiny dwarf galaxies or the shattered remains of galactic collisions. But this spiral is massive and intact, offering a pristine window into an era when the cosmos was just finding its footing. Its stars hold chemical signatures of that primordial time, with fewer heavy elements than modern galaxies, a clue that it formed from nearly pure hydrogen and helium, the universe's original building blocks. Then there's the puzzle of its rotation. Spiral arms are essentially density waves, patterns that move through a galaxy's disk like ripples in a pond. Over time, these waves should weaken or distort, especially in turbulent environments. But this galaxy's rotation curve, the way its stars and gas move, matches modern spirals almost exactly. It's as if the physics that govern galaxy evolution worked differently here, or some unseen force hit the brakes on time itself. Perhaps the most tantalizing possibility is that we're witnessing a rare cosmic equilibrium. Like a spinning top that refuses to fall, this galaxy might exist in a perfect balance between destruction and renewal. Its spiral arms could be constantly fed by streams of cold gas, replenishing what the environment steals away, while its dark matter halo acts as a stabilizer. If true, it's a reminder that the universe has pockets of order hidden within its chaos, places where the rules bend, and the improbable becomes real. What makes this time capsule so valuable isn't just its defiance of expectations, but what it reveals about the early universe's diversity. For decades, we assumed the cosmos was a simpler place back then, with galaxies evolving along predictable paths. But this spiral proves there were outliers, exceptions that challenge our neat timelines. It's forcing astronomers to ask, was this galaxy a fluke, or are we just beginning to see the true complexity of the universe's youth? Every new observation peels back another layer, showing us a past far more vibrant and unpredictable than we ever imagined. Gravity is supposed to be the great equalizer in the cosmos, the force that shapes galaxies into predictable forms over time. But what if something unseen is tilting the scales? The impossible spiral's defiance of cosmic norms has led some scientists to suspect hidden gravitational players at work, forces bending the rules of space-time to preserve its delicate structure. Could invisible black holes lurk in its shadows, their immense gravity acting like cosmic anchors? Or might exotic forms of matter, stranger than anything we've yet discovered, be warping the fabric of reality around it? Simulations offer the first tantalizing clues. When astrophysicists tried to recreate this galaxy in supercomputer models, they hit a wall. Standard physics couldn't produce such a pristine spiral in such a chaotic environment. But when they introduced hypothetical mid-sized black holes along the galaxy's outskirts, something remarkable happened. These unseen giants, each hundreds of thousands of times the mass of our Sun, seemed to sculpt the surrounding gas into stable spiral patterns, their gravity acting like invisible fingers guiding the flow. Unlike the supermassive black holes at galactic centers, these stealthy intermediates wouldn't emit detectable radiation, making them nearly impossible to spot directly. Yet their influence could explain how the spiral arms resist disruption, as if shielded by an unseen gravitational lattice. Then there's the exotic matter hypothesis. Some theorists suggest this galaxy might be threaded with dark baryons, a proposed form of matter that interacts with ordinary atoms only through gravity. Unlike dark matter, which clumps in vast halos, dark baryons could be distributed in precise filaments, reinforcing the spiral structure like cosmic rebar. Others speculate about even stranger possibilities, theoretical particles like actions or WIMP, which might form dense knots along the arms, stabilizing them against external chaos. The most mind-bending idea comes from modified gravity theories. What if Einstein's equations break down under extreme conditions, allowing gravity to behave differently in the early universe's dense environments? Certain alternative models, like modified Newtonian dynamics, suggest gravity could grow stronger where matter is sparse, precisely the conditions in this galaxy's outer reaches. If true, it might explain why the spiral arms hold their shape despite the surrounding turmoil, as if space itself is stiffer there, resisting distortion. Of course, these are all provisional answers. The real test will come when next-generation telescopes like the James Webb Space Telescope or the upcoming Extremely Large Telescope train their sights on this cosmic rebel. Will they find the fingerprints of hidden black holes in the subtle wobbles of nearby stars? Could spectral analysis reveal the ghostly presence of exotic matter? Every new observation peels back another layer of the mystery, reminding us that the universe still holds forces we've yet to name, and that sometimes the most impossible things are just waiting for us to look closer. When Hubble first turned its gaze toward this cosmic anomaly, even its advanced optics struggled to make sense of what they were seeing. The images that came back were breathtaking crystal-clear spirals etched against the blackness of deep space, their symmetry so perfect they looked almost artificial. But hidden in those pixels were contradictions that left astronomers scratching their heads. The galaxy's star formation rate was off the charts, birthing new stars at a pace 10 times faster than our Milky Way. Yet its core was eerily calm, lacking the violent bursts of energy typically seen in such prolific stellar nurseries. Zooming in on the spiral arms revealed another puzzle. While most young galaxies from this epoch show a messy, clumped distribution of stars, this one had distinct, well-defined lanes of star formation, like a master painter had carefully brushed them into place. Even stranger was the chemistry. Spectroscopic analysis detected surprisingly low levels of heavy elements, the kind forged in supernova and scattered across galaxies over time. This suggested the galaxy was drawing from a nearly pristine reservoir of gas, untouched by the pollution of earlier stellar generations. It was like finding a gourmet kitchen in the middle of a construction site, stocked with ingredients no one had delivered yet. The most startling revelation came from Hubble's ultraviolet sensors. They spotted massive, young stars blazing along the outer edges of the spiral arm stars that shouldn't exist there. In modern spirals, such hot, short-lived stars typically form closer to the center, where gas is densest. Their presence in the outskirts hinted at some unseen mechanism efficiently funneling gas outward, like an invisible hand redistributing the galaxy's raw materials. Some researchers speculate this could be the work of rogue supernova, their explosive kicks sending shockwaves that push gas toward the edges. Others wonder if the galaxy's dark matter halo is sculpting these flows, its gravity guiding the gas along hidden pathways. Then there's the mystery of the missing middle-aged stars. Hubble's deep field exposures revealed populations of ancient stars and newborn ones, but a curious gap in between, as if star formation had paused for 1 billion years before suddenly reigniting. This isn't just unusual, it's unprecedented. Galaxies don't typically take naps in their prime. One provocative theory suggests the galaxy might have undergone a near-fatal collision early on, stripping away its gas and halting star formation until fresh material could accumulate again. If true, it would mean this spiral isn't just surviving chaos, it's thriving because of it, turning catastrophe into rebirth. Every pixel from Hubble adds another layer to the enigma. The telescope's keen eye even spotted delicate tendrils of gas stretching between the spiral arms, filaments so faint they're almost ghostly. These could be the remnants of past mergers or the signatures of gas being pulled in from intergalactic space, a cosmic lifeline keeping the spiral young. What's clear is that this galaxy isn't following the script. It's a reminder that the universe reserves the right to surprise us, and that sometimes the most profound discoveries begin with a single, impossible image. Dark matter isn't the only explanation on the table. Some scientists are questioning whether we've been looking at this cosmic puzzle all wrong. Imagine spending decades searching for a missing key, only to realize the door might not have been locked in the first place. That's the essence of the debate swirling around this impossible spiral. Could its defiance of cosmic rules stem not from invisible matter, but from flaws in our very understanding of gravity itself? One of the most provocative alternatives comes from a theory called modified Newtonian dynamics, or MND. Instead of invoking dark matter to explain why galaxies hold together, MND suggests that gravity behaves differently at extremely low accelerations, like those found in the outer reaches of galaxies. In this view, the impossible spiral's pristine arms might simply be a consequence of gravity's hidden rules, its stars moving in ways that seem impossible only because our equations are incomplete. Supporters point to oddities in other galaxies where rotation curves don't match predictions, as if some unseen hand is gently tweaking the laws of physics in deep space. But MND faces its own hurdles. While it explains some galactic quirks, it struggles with larger-scale cosmic structures like galaxy clusters, where dark matter's gravitational fingerprints are harder to ignore. Critics argue that if MND were correct, we'd expect to see far more spirals like this one, yet they remain vanishingly rare. Then there's the elephant in the room, Einstein's theory of general relativity, which has predicted everything from black holes to gravitational waves with astonishing precision. Throwing it out would mean rewriting much of modern physics, a step many scientists aren't ready to take without ironclad evidence. Another fringe idea takes inspiration from quantum physics. Could the galaxy's stability arise from something even stranger, like a sea of ultra-light particles called actions, theorized to permeate the universe? These ghostly particles might form intricate, wave-like patterns on galactic scales, their subtle push and pull reinforcing spiral arms like an invisible loom weaving starlight into shape. It's a wild notion, but not entirely implausible. Actions are already candidates for dark matter, and certain models suggest they could condense into cosmic-scale structures we've never thought to look for. Then there's the multiverse angle. Some theorists speculate that this galaxy might sit at the intersection of unseen dimensions, its gravity leaking into hidden layers of reality that subtly alter its behavior. While this sounds like science fiction, similar ideas have been floated to explain other cosmic anomalies, like the puzzlingly weak strength of gravity compared to other fundamental forces. If true, it would mean the impossible spiral isn't just breaking rules, it's playing by an entirely different rulebook from another dimension, the most sobering possibility. That we're seeing a statistical fluke, a 1 in a billion cosmic accident where random factors align to preserve this spiral against all odds. After all, the universe is vast enough that even the most improbable events occasionally occur. But most astronomers dismiss this as a cop-out. The galaxy's precise structure, its placement in a high-density cluster, and its chemical fingerprints all suggest something deeper at work, a hidden mechanism waiting to be uncovered. What unites these theories isn't just their boldness, but their willingness to question foundational assumptions. Whether the answer lies in modified gravity, exotic particles, or forces we've yet to name, the impossible spiral is more than a curiosity. It's a catalyst pushing us to rethink the bedrock principles of cosmology. And that's how science moves forward, not by clinging to old ideas, but by daring to imagine that the universe might still have a few surprises up its sleeve. Galactic mergers are usually cosmic wrecking balls, violent encounters that shred delicate spiral arms into chaotic streams of stars. But what if, just once, a collision played out differently? The Shipwreck Theory dares to suggest that this impossible spiral didn't survive despite a collision. It thrived because of one. Picture two galaxies sweeping toward each other in the early universe, their trajectories aligning with freakish precision. Instead of a catastrophic crash, their gravitational dance could have been so perfectly balanced that it sculpted the chaos into order, leaving behind a single, flawless spiral where two messy galaxies once existed. The idea isn't as far-fetched as it sounds. Computer simulations show that under rare conditions, mergers can create temporary spiral patterns as gas and stars are flung outward in graceful arcs. Normally, these structures dissolve within a few 100 million years. But if one galaxy was rich in gas while the other had a dense core, their combination might have stabilized the spiral, like two imperfect puzzle pieces locking together to form something unexpectedly whole. The key would be the smaller galaxy striking at just the right angle, not head-on, but a glancing blow that imparts spin without total destruction. There's tantalizing evidence hidden in the galaxy's outskirts. Telescopes have detected faint stellar streams, wispy ribbons of stars arcing beyond the spiral arms. These could be the ghostly remains of the smaller galaxy, stretched into celestial tinsel by the merger. Even more telling is the spiral's unusually bright core, which glows with the concentrated light of countless stars. Such overstuffed centers are classic fingerprints of galactic collisions, where incoming stars pile up like cars in a cosmic traffic jam. Yet the Shipwreck Theory has its skeptics. If a merger created this spiral, why don't we see more like it? The early universe was a riot of galactic collisions, yet pristine spirals from that era remain vanishingly rare. Some astronomers argue that the very forces that should stabilize a post-merger spiral, like turbulence and shock waves, would also disrupt its delicate arms over time. Unless, of course, something else stepped in to preserve it. That's where dark matter re-enters the story. If the colliding galaxies had lopsided dark matter halos, their combined gravity might have acted like a mold, shaping the gas into enduring spiral patterns. Alternatively, the collision could have triggered a burst of star formation so intense that newborn stars reinforced the arms, their collective gravity knitting the spiral tighter even as the merger's chaos tried to tear it apart. The most fascinating twist, this galaxy might not be done evolving. If the Shipwreck Theory is correct, we could be witnessing a fleeting cosmic moment, a spiral caught in the act of formation, destined to eventually fray into a more common elliptical shape. Or perhaps it's found a perfect equilibrium, a rare state where destruction and creation balance so precisely that time itself seems to pause. Either way, it's a reminder that even in the violent arena of galactic collisions, the universe occasionally creates beauty from the wreckage. The James Webb Space Telescope is rewriting the rules of cosmic observation, and this impossible spiral galaxy is first in line for its revolutionary gaze. Unlike Hubble, which sees primarily invisible and ultraviolet light, Webb's infrared eyes pierce through veils of dust and time, revealing details hidden since the galaxy's infancy. Already, early observations have upended expectations. Where Hubble saw smooth spiral arms, Webb's sharper vision detects intricate structures, delicate tendrils of gas, pockets of newborn stars wrapped in stellar nurseries, and something even more unexpected: tiny, dense star clusters tucked between the arms like cosmic stepping stones. These clusters shouldn't exist in a galaxy this young, yet there they are, glowing defiantly in Webb's data. One theory suggests these clusters are the galaxy's secret weapon. Formed during its chaotic early years, they could act as gravitational anchors, their collective mass stabilizing the spiral arms against disruption. Webb's spectrographs are now analyzing their chemical makeup, searching for traces of rapid star formation that might explain their presence. Preliminary results hint at something startling. These stars contain barely any heavy elements, as if they formed from gas untouched by previous generations of supernova. That would mean the galaxy had access to pristine reservoirs of material long after its peers had polluted their surroundings, a cosmic loophole allowing it to stay young while the universe aged around it. But Webb's most tantalizing discovery lies in the galaxy's core. Where Hubble saw only a quiet center, Webb's infrared sensors detected an eerie glow, not from a supermassive black hole, but from thousands of dim, ancient stars packed tighter than thought possible. Their arrangement defies models of galactic evolution. Such dense stellar configurations typically appear only after billions of years of gravitational settling. Yet here they are, crowding the galaxy's heart as if time ran differently in this pocket of the cosmos. Some astronomers speculate these stars might be relics of the galaxy's violent youth, survivors of a primordial collision that compressed them into this bizarre configuration. Then there's the dust. Webb's mid-infrared instrument has mapped sprawling clouds of complex organic molecules swirling through the spiral arms, molecules usually associated with much older galaxies. Their presence suggests this galaxy mastered efficient star formation early, recycling material without the wasteful explosions that typically scatter heavy elements into intergalactic space. It's as if the spiral found a way to farm stars gently, nurturing them over eons rather than in fits and starts. Webb's greatest contribution might be temporal. By measuring the galaxy's light with unprecedented precision, it's refining our estimate of its age, placing its formation shockingly close to the Big Bang. Each new data download feels like rewinding a cosmic film reel, revealing frames of universal history we never knew existed. And the more we see, the clearer it becomes. This isn't just an oddball galaxy. It's a Rosetta Stone for deciphering the universe's hidden rules, written in starlight and waiting for us to decode. Star formation is the heartbeat of a galaxy, the pulse that dictates its life and evolution. But in this impossible spiral, that heartbeat is erratic, sometimes racing, sometimes skipping a beat entirely. Most spiral galaxies follow a predictable rhythm. Dense clouds of gas collapse under gravity, ignite into stars, and light up their spiral arms in a slow, steady dance. This cosmic rebel, however, defies the pattern. Its star formation isn't just uneven, it's almost rebellious, flaring up in bursts so intense they should have torn the galaxy apart, then falling eerily silent for epochs at a time. Take the outer arms, where Hubble and Webb spotted something bizarre. Vast stellar nurseries glowing with newborn stars, but no trace of the older generations that should have preceded them. It's like walking into a forest and finding only saplings, no mature trees in sight. One explanation is that the galaxy is drawing from reservoirs of pristine gas, untouched by previous star formation. Without the heavy elements forged in supernova, the gas remains ultra-efficient at collapsing into stars, creating these isolated pockets of youth in an otherwise ancient galaxy. Then there's the core, where star formation should be fiercest. Instead, it's a graveyard of ancient stars, their light faint and red, with almost no new births to speak of. This inversion, a galaxy birthing stars on its fringes while its center lies dormant, is virtually unheard of. Some theorists suggest the galaxy's central black hole, though quiet now, might have had a violent past. A long-ago outburst could have blown away the core's gas, starving it of star-making material while leaving the outer arms untouched. Others propose that the spiral's unique rotation patterns are funneling gas outward, like a cosmic sprinkler system irrigating only the edges. The most tantalizing clue comes from the galaxy's missing supernova. With such rampant star formation, astronomers expected to find the remnants of countless exploded stars, the usual fate of massive, short-lived suns. Yet the galaxy's chemical makeup tells a different story. It's oddly deficient in the heavy elements these explosions produce, as if most massive stars here are vanishing without the expected fireworks. One radical idea is that they're collapsing directly into black holes, skipping the supernova stage entirely. If true, it would mean this galaxy operates by a different stellar rulebook, one where stars vanish into the dark rather than lighting up their deaths for all to see. What makes these quirks so fascinating isn't just their strangeness, but what they reveal about the galaxy's resilience. Most galaxies with such chaotic star formation would have self-destructed by now, their spiral arms shredded by the violent births and deaths of their stars. Yet this one endures, its structure pristine. The secret might lie in balance, a delicate equilibrium where star formation is just turbulent enough to replenish the spiral arms, but not so violent that it tears them apart. It's a cosmic tightrope walk, and against all odds, this galaxy has been performing it for billions of years. Every irregularity in its star formation is a clue, a piece of a puzzle we're only beginning to assemble. Whether it's the pristine gas, the missing supernova, or the oddly placed stellar nurseries, each anomaly hints at a deeper truth. This galaxy isn't just surviving the chaos of the universe. It's thriving by rewriting the rules. Most galaxies in dense clusters resemble boxes in a ring, constantly jostling, colliding, and emerging bruised, but this impossible spiral. It's more like a figure skater, weaving through a crowded rink with impossible precision, its spiral arms trailing behind it like a celestial gown. Tracing its path through the cosmos reveals something extraordinary. While neighboring galaxies slam together in violent mergers, this one glides past them, close enough to feel their gravitational pull but never close enough to be torn apart. It's a cosmic tightrope act, and the galaxy has been performing it for billions of years. The secret lies in its trajectory. Detailed simulations show it's not orbiting the cluster's center like most galaxies. Instead, it's on a high-speed hyperbolic path, a celestial slingshot maneuver that keeps it from settling into the chaos below. Think of it as a comet whipping around the sun, using gravity's pull to accelerate without being captured. Only in this case, the galaxy isn't just passing by. It's threading the needle between massive neighbors, each near miss imparting just enough energy to keep it dancing on the edge of destruction. Even more fascinating are the ripples it leaves in its wake. As the spiral moves, its gravity tugs on surrounding gas, creating shimmering wakes of star formation like cosmic breadcrumbs marking its passage. Some of these trails glow with newborn stars, suggesting the galaxy is seeding the cluster with fresh stellar nurseries as it travels. Others show eerie voids where gas has been stripped away, as if the spiral is drinking from the cosmic rivers around it to sustain its own star-forming frenzy. Then there's the mystery of its timing. Normally, a galaxy moving this fast would have escaped its cluster long ago. Yet here it remains, locked in a gravitational waltz that defies expectations. Some researchers suspect the cluster's dark matter halo might be warping space around it, bending the galaxy's path into a lazy arc that keeps it circling without ever fully joining the fray. Others propose it's caught in a rare resonance with multiple massive galaxies, their combined gravity creating a sort of celestial traffic circle that guides the spiral safely through the chaos. What's certain is that this galaxy isn't just surviving, it's thriving on the edge of disaster. Every close encounter seems to inject fresh gas into its spiral arms, fueling new generations of stars while the gravitational tides sculpt its structure ever sharper. It's a reminder that in the cosmos, chaos and beauty aren't opposites sometimes, they're partners in an endless, impossible dance. The light we're seeing from this impossible spiral isn't just a snapshot, it's a time capsule, a beam that's been racing through the void for over 12 billion years before finally landing in our telescopes. That journey has left its mark in the form of redshift, the stretching of light waves as the universe expands, and embedded in that faint glow are secrets about the galaxy's age, its motion, and the turbulent neighborhood it calls home. When astronomers first measured its redshift, the numbers didn't just place it far away, they placed it in an era when the universe was still in its reckless youth, a time when most galaxies were supposed to be messy, half-formed things. Yet here it was, a fully realized spiral, its light telling a story that contradicted everything we thought we knew about cosmic evolution. Decoding that story starts with spectral lines, the unique fingerprints elements leave in starlight. As this galaxy's light passed through clouds of gas on its way to us, certain wavelengths were absorbed, leaving dark gaps in the spectrum. The positions of those gaps reveal not just what the galaxy is made of, but how fast it's moving. The surprise, while most galaxies at this distance show extreme redshift racing away from us as the universe expands, this one has subtle anomalies. Parts of it seem to be moving at slightly different speeds, as if the spiral is spinning faster than models predict, its outer arms whipping around like a cosmic carousel. Then there's the environment. Redshift measurements pinpointed the galaxy's location in a protocluster, a dense knot of early galaxies that should have been a gravitational minefield. But the spectral lines tell another story. Despite the chaos around it, the spiral's gas shows remarkably little turbulence. It's as if the galaxy found a quiet eddy in the cosmic river, a pocket of calm where it could refine its perfect shape undisturbed. Even more puzzling are the absorption lines from foreground gas clouds. They're pristine, lacking the heavy elements we'd expect from a region littered with supernova debris. This suggests the spiral exists in a bubble of unusually clean space, a haven where it could draw on unsullied gas to fuel its star formation. The most tantalizing clue lies in the Lyman alpha line, a signature of hydrogen that's often scattered or absorbed in young galaxies. Here it shines through with unexpected clarity, hinting that the galaxy's early stars ionized their surroundings with remarkable efficiency, carving out transparent pathways for their light to escape. That's another anomaly. Most galaxies from this epoch are shrouded in opaque fog, their light struggling to pierce the primordial haze. Yet this one gleams like a beacon, its light reaching us with a clarity that defies its era. Every wavelength tells a story, and together they paint a portrait of a galaxy that's not just surviving the chaos of the early universe, but mastering it. The redshift doesn't just measure distance, it's a window into a place where the rules were rewritten, where a spiral could flourish against all odds. And as newer telescopes like JWST peer even deeper into these spectral fingerprints, who knows what other secrets they'll uncover? The light has traveled 12 billion years to bring us this message. We're only just beginning to understand what it's trying to say. Supercomputers have thrown everything they've got at this cosmic rebel, and it's still winning. Picture the most powerful simulations in astrophysics algorithms that recreate galaxy formation down to the finest details. Models that have predicted everything from colliding black holes to the birth of star clusters. Yet when scientists feed this spiral's parameters into those same programs, the results are baffling. Either the simulated galaxy collapses into a shapeless blob, or its spiral arms unravel within a few billion virtual years. Nothing in our digital universe can match the real thing's impossible persistence. And that failure is forcing astronomers to confront a humbling truth. somewhere in our understanding of galaxies, there's a missing piece. The trouble starts with turbulence. In simulations, galaxies forming in dense clusters like this one should be cosmic train wrecks. Their gas stirred into chaos by nearby gravitational disruptions, their stars scattered like billiard balls after a break shot. Yet this spiral's arms remain pristine, as if shielded by some unseen hand. Researchers have tweaked every variable, adjusting dark matter density, fine-tuning star formation rates, even accounting for hypothetical gas flows from intergalactic filaments. The closest they've come is a fleeting spiral that briefly appears before dissolving, like a sandcastle resisting the tide for just a moment too long. One major roadblock is the galaxy's star formation efficiency. In most simulations, gas either forms stars too aggressively, creating a starburst that blows away remaining material, or too slowly, leaving the galaxy anemic and unstable. This spiral somehow strikes a perfect balance, producing stars at a rate that sustains its structure without self-destructing. Some theorists suspect small-scale physics might hold the key processes like magnetic fields or supernova feedback operating at resolutions too fine for current simulations to capture. It's like trying to predict a hurricane's path while ignoring individual raindrops. The tiny details might add up to something critical. Then there's the mystery of angular momentum. Spiral arms rely on a delicate transfer of rotational energy from the galaxy's core to its outskirts, a dance that simulations struggle to replicate naturally. Most models require artificial fixes to maintain spiral structures, like manually injecting extra rotation or suppressing disruptive mergers. But the real universe doesn't have a programmer tweaking the code. This galaxy achieved its symmetry without cosmic cheat codes. The discrepancy suggests our simulations might be oversimplifying how gravity interacts with gas on galactic scales, or missing some fundamental process that stabilizes rotating systems. Perhaps the most telling failure involves dark matter. Even when simulations include elaborate dark matter halos, they can't explain how this spiral's halo deflects disruptions so precisely. Some teams have tried adding speculative dark matter, subhalos, smaller clumps orbiting the main halo, to act as gravitational buffers. Others have toyed with dark matter that interacts weakly with itself, creating internal friction that dampens external shocks. So far, no configuration matches the galaxy's real-world resilience. These aren't just technical hurdles, they're clues. Every simulation crash, every implausible result is a signpost pointing toward physics we haven't yet grasped. The galaxy's defiance of digital recreation doesn't mean our models are worthless. It means they're incomplete, like a map with whole continents left blank. And that's where the real excitement lies, because when simulations fail, it's often the universe's way of whispering, "Look closer. There's something here you haven't seen yet." For astronomers, that's not a setback, it's an invitation to discovery. Could the universe be playing the ultimate trick on us? Among the wildest explanations for this impossible spiral is the idea that we're not seeing a real galaxy at all, but a cosmic mirage, a trick of light warped by gravity's invisible hand. Einstein's theory of general relativity predicted this phenomenon over a century ago. Massive objects bending space-time like a bowling ball on a trampoline, distorting the path of light from distant objects behind them. Normally, this gravitational lensing creates telltale signs, stretched arcs, smeared duplicates, or halo-like rings around the lensing object. But what if the alignment was so precise, the distortion so subtle, that it sculpted a perfect spiral illusion from a far messier reality? The first clue lies in the galaxy's surroundings. It sits in a dense cluster packed with dark matter, exactly the kind of place where lensing effects run rampant. Simulations show that under freakishly specific conditions, multiple lensing galaxies could work in concert, their combined gravity acting like a funhouse mirror that twists a background galaxy's light into a deceptively symmetrical shape. Imagine holding a magnifying glass over a crumpled piece of paper. At just the right angle, the wrinkles smooth out, revealing what looks like a flawless surface. Could nature be pulling a similar sleight of hand here? Yet the mirage theory hits snags under scrutiny. For one, gravitational lensing typically magnifies the background object, making it appear brighter. This spiral, though, shows no unusual luminosity. Its brightness matches what we'd expect for a galaxy of its size and distance. Even more damning is the absence of telltale lensing artifacts. There's no smeared duplication of the spiral's core, no distorted copies hovering nearby. If this were a lensed illusion, astronomers argue, we'd see at least some faint echoes in the data. Then there's the chemistry problem. Spectroscopic analysis reveals the galaxy's stars have distinct metallicity's chemical fingerprints that would be scrambled if lensing were warping light from multiple sources. It's the difference between looking at a single painting and a collage of fragments. The spiral spectral lines are too coherent to be a composite, but the most compelling counterargument comes from the galaxy's motion. Lensed images are frozen snapshots. They can't account for the spiral's intricate rotation patterns, where stars on one side move toward us while those on the other side recede. That kind of dynamic structure would require the lens to somehow animate the illusion, a feat beyond even relativity's wildest tricks. Still, the mirage hypothesis isn't entirely dead. Some researchers suggest a middle ground. Perhaps lensing isn't creating the spiral from scratch, but enhancing its already present structure. A slight gravitational nudge could sharpen faint arms into bold strokes, like an artist tracing over pencil lines in ink. If true, it would mean we're seeing a real galaxy, just one that's been cosmically photoshopped. Whether mirage or marvel, this galaxy's defiance forces us to confront the limits of our cosmic vision. In a universe where space-time bends and light lies, the only certainty is uncertainty. And that's what makes the hunt so thrilling. Every time we think we've pinned down reality, the cosmos reminds us to look twice. Most galaxies sing. Across the electromagnetic spectrum, they hum with radio waves generated by swirling gas, screaming quasars, and the afterglow of supernova. But this spiral, it's eerily mute. When radio telescopes like the Very Large Array turned their dishes toward it, they picked up barely a whisper, just a faint hiss of background noise where there should have been a cosmic symphony. This silence isn't just unusual, it's borderline unnatural. Spirals like our Milky Way typically broadcast their presence loud and clear, their radio emissions tracing the dance of charged particles trapped in magnetic fields. So why is this one holding its breath? One possibility is that the galaxy's black hole has gone dormant. At the heart of most spirals, supermassive black holes act like cosmic engines, their gravitational pull accelerating nearby matter to near light speeds. This process generates powerful radio jets, beams of charged particles that can stretch for millions of light years. But here, the core is suspiciously quiet. No jets, no bursts, just a black hole seemingly in deep hibernation. Some astronomers speculate it might have exhausted its fuel supply early, starving in a gas-poor environment while the rest of the galaxy carried on. Others wonder if something more exotic is at work, like a black hole spinning at just the right angle to suppress jet formation, its gravity funneling energy away in invisible directions. Then there's the gas problem. Radio waves often come from regions where gas is being violently stirred, colliding clouds, newborn stars, or supernova shockwaves. Yet this galaxy's gas appears strangely calm, Observations reveal vast reservoirs of hydrogen, but they're not churning with the expected turbulence. It's as if the gas is trapped in some cosmic deep freeze, unable to generate the friction that would normally light up radio telescopes. One theory points to the galaxy's unique magnetic fields. If they're aligned in just the right configuration, they might be stifling particle acceleration, preventing the usual radio chatter. Imagine trying to start a fire with wet wood. The fuel is there, but the conditions won't let it ignite. The most unsettling explanation involves dark matter again. Certain theories suggest that dark matter particles could interact with ordinary matter in ways we don't yet understand, perhaps absorbing energy that would otherwise become radio waves. If this galaxy's dark matter halo has unusual properties, it might be acting like an electromagnetic sponge, soaking up the signals before they can escape. It's a long shot, but not impossible. After all, the universe has surprised us before. Whatever the cause, this radio silence is more than a curiosity, it's a clue. In a cosmos where noise is the norm, quiet can be just as revealing. The absence of radio waves forces us to ask new questions, to consider possibilities we might have otherwise ignored. And that's how science moves forward, not just by listening to the universe's shouts, but by paying attention to its whispers too. When faced with something as inexplicable as this spiral galaxy, it's tempting to let imagination run wild, to leap beyond known physics and wonder if we're glimpsing something constructed. The idea of alien megastructures isn't new. Back in the 1960s, physicist Freeman Dyson speculated about advanced civilizations harnessing entire stars for energy, building vast shells or swarms of orbiting collectors. More recently, the bizarre dimming of Tabby's star sparked similar speculation, with some wondering if its irregular light patterns hinted at colossal artificial objects passing in front of it. Could this impossibly perfect spiral then be something similar, a cosmic sculpture on a scale we can barely comprehend? For a moment, let's play with the thought. Picture a civilization so advanced it doesn't just inhabit a galaxy, but reshapes it. Instead of random collisions and chaotic mergers, they engineer stability, bending gravity and matter to their will. The spiral arms, perhaps vast stellar nurseries cultivated for resources, or even art on a galactic canvas. The eerie silence in radio waves, a deliberate cloaking, a civilization so sophisticated it no longer leaks detectable energy. It's a thrilling idea, one that taps into our fascination with the unknown and the limits of technology. But here's the catch: extraordinary claims demand extraordinary evidence. And so far, there's none. No unnatural spectral lines, no geometric precision in the spiral arms, no telltale signs of energy harvesting or waste heat. The galaxy's structure, while baffling, still operates within the known laws of physics, just pushed to their limits. Even the most exotic explanations, from dark matter to modified gravity, are rooted in natural phenomena. That's the heart of science, exploring the improbable while dismissing the impossible until proven otherwise. That said, the megastructure hypothesis isn't entirely useless. It serves as a reminder of how little we truly understand about the universe. Every time we encounter something inexplicable, it stretches our imagination, forcing us to ask, what if? Even if the answer is mundane, the question itself can lead to unexpected discoveries. After all, some of history's greatest scientific leaps began as wild guesses. The key is knowing when to rein them in. So while we might smile at the idea of cosmic architects, the real wonder lies in the galaxy's natural defiance. It challenges us to dig deeper into the laws we think we know, to question assumptions, and to stay open to the universe's endless capacity to surprise. Whether through dark matter, unseen physics, or some yet undreamed mechanism, the truth is likely stranger than any fiction we could invent. And that's the beauty of the cosmos. It doesn't need aliens to be awe-inspiring. No galaxy exists in isolation, and this cosmic rebel is no exception. Its impossible spiral arms may owe their survival to the chaotic neighborhood it calls home. Surrounding it are galaxies locked in gravitational combat, their violent mergers and near misses shaping the environment like cosmic weather. Yet amid this turbulence, the impossible spiral remains unscathed, almost as if it's found shelter in the storm. The key to understanding its defiance might lie not just in the galaxy itself, but in the intricate dance of its neighbors. Take the massive elliptical galaxy just 500,000 light-years away, a behemoth 10 times its size, whose gravity should have ripped the spiral apart long ago. Instead of destruction, their interaction seems almost symbiotic. Observations reveal faint streams of gas arcing between them, like invisible bridges feeding the spiral fresh material. Some astronomers speculate this giant neighbor acts as a gravitational shield, its immense bulk deflecting incoming interlopers that might otherwise disrupt the spiral's delicate arms. It's a cosmic version of a mountain shielding a valley from harsh winds, an accidental protector in the chaos. Then there's the swarm of dwarf galaxies circling the outskirts, tiny but numerous. In most clusters, these small galaxies are like buzzing gnats, their cumulative tugs distorting larger structures over time. Here, though, they seem to orbit in uncanny harmony, their paths aligned in a way that minimizes chaos. Computer simulations suggest their collective gravity might actually reinforce the spiral's rotation, like tiny gears synchronizing to keep a larger machine running smoothly. The real puzzle lies in the gas. Intergalactic space in this region is crisscrossed with filaments of cold hydrogen rivers of raw star, making fuel flowing through the void. Normally, such gas would be heated to oblivion by the cluster's violent environment, but here it remains eerily cool. Some researchers think the spiral's dark matter halo might be funneling these gas streams directly into its arms, like cosmic irrigation channels feeding a garden. Others point to shock fronts from nearby galaxy collisions, which could be compressing the gas into dense, star-forming pockets just where the spiral needs them most. What emerges is a picture of unlikely balance. This galaxy isn't just surviving its neighborhood, it's thriving because of it, turning chaos into an unexpected advantage. The same forces that should have shredded it may instead be the very things preserving its impossible beauty. And that raises a tantalizing question. Are we looking at a cosmic fluke or a hidden rule of galactic survival we've only just begun to uncover? At the heart of most spiral galaxies, including our own Milky Way, lurks a supermassive black hole, a gravitational monster millions or even billions of times heavier than the Sun. These cosmic behemoths aren't just destructive forces, they're thought to play a crucial role in shaping their galaxies, acting like invisible anchors around which stars and gas whirl in an orderly dance. So where does this leave our impossible spiral? If it follows the rules, there should be a supermassive black hole at its core, quietly orchestrating the chaos around it. But when astronomers peered into its center, they found something unexpected, a black hole that defies expectations just as boldly as the galaxy itself. The first clue came from the galaxy's motion. Stars near the core whip around at dizzying speeds, their orbits hinting at the presence of something massive. Yet when researchers calculated the black hole's likely mass, the numbers didn't add up. It's far smaller than models predict for a galaxy of this size, as if it stopped growing midway through its cosmic adolescence. Even stranger, it's eerily quiet. Most supermassive black holes in spirals are active feeders, slurping down gas and dust and belching out torrents of energy as bright quasars or radio jets. This one, though, is practically dormant, emitting barely a whisper of radiation. It's like finding a sleeping dragon curled at the heart of a volcano that should be erupting. The absence of activity might be the key to the spiral's survival. In most galaxies, a feeding black hole creates havoc. Its radiation and jets heat surrounding gas, preventing it from cooling and forming new stars. But here, the black hole's silence could be preserving the delicate balance needed for those pristine spiral arms. Without violent outbursts disrupting the galaxy's gas, star formation can proceed in an orderly rhythm, replenishing the spiral structure instead of tearing it apart. Some theorists suggest the black hole might be in a rare state of equilibrium, its hunger perfectly matched by the trickle of gas falling into it, just enough to sustain it, but not enough to trigger a destructive feeding frenzy. Then there's the spin. Black holes aren't just defined by their mass, they also rotate, some whirling at nearly the speed of light. Simulations show that a rapidly spinning black hole can warp space-time around it, creating a sort of gravitational vortex that stabilizes nearby orbits. If this galaxy's black hole is spinning at just the right rate, it might be acting like a gyroscope, steadying the entire galactic disk and keeping those spiral arms razor-sharp. The idea isn't as far-fetched as it sounds. Recent observations of other galaxies suggest a link between black hole spin and galactic structure, though none as extreme as this case. The most tantalizing possibility, the black hole might not be working alone. Some models propose it's part of an unseen duo, a binary black hole system where two massive objects orbit each other in a tight, rhythmic dance. Such pairs are thought to form during galaxy mergers, and their gravitational interplay could explain the spiral's unusual stability. Like two conductors leading an orchestra, they might synchronize the motions of stars and gas, preventing the kind of chaos that usually unravels spiral arms in dense environments. There's even a wilder variation, a kicked black hole, one sent recoiling after a violent merger, its off-center position creating asymmetrical forces that somehow reinforce the spiral instead of destroying it. Yet for all these theories, the black hole's role remains a puzzle. It's too small, too quiet, and too calm to fit the mold, yet the galaxy around it thrives. Maybe it's not the anchor we expected, but something far stranger, a black hole that's learned to coexist with its galaxy in perfect harmony, a silent partner in an impossible dance. Whatever the truth, one thing is clear: this cosmic rebel isn't just breaking the rules. It's showing us that black holes, like the galaxies they inhabit, still have secrets to reveal. Quantum mechanics and galaxy formation seem like concepts from opposite ends of the cosmic scale, one governing the subatomic world, the other shaping structures millions of light years across. Yet when faced with a spiral galaxy that defies every classical explanation, scientists are forced to ask, could the universe's smallest rules be influencing its grandest designs? At the heart of this question lies a radical idea that quantum effects, typically confined to the realm of particles and probabilities, might somehow scale up to leave fingerprints on an entire galaxy's structure. Consider the galaxy's spiral arms. In the quantum world, particles don't move in neat orbits but exist as probability clouds, their positions fuzzy until measured. Some theorists suggest that on cosmological scales, dark matter, if it's made of ultralight particles like actions, might exhibit similar wave-like behavior. These hypothetical particles could form interference patterns across vast distances, their peaks and troughs sculpting the galaxy's gas into those impossibly precise arms. It's as if the spiral isn't just shaped by gravity, but by an invisible quantum blueprint, a cosmic standing wave frozen in starlight. Then there's entanglement, quantum physics' spookiest phenomenon, where particles remain mysteriously linked across space. Could something analogous be happening here? Imagine the galaxy's stars and gas as part of an entangled system, their motions coordinated not just by gravity but by some deeper, non-local connection. While this sounds like science fiction, recent work in quantum gravity explores how entanglement might influence the large-scale structure of spacetime itself. The spiral's eerie symmetry could be a macroscale echo of processes we've only glimpsed in particle colliders. The most tantalizing clue comes from the galaxy's rotation. Quantum vortices whirlpools seen in superfluid helium share uncanny similarities with the dynamics of spiral arms. Both exhibit stable, long-lived patterns that resist disruption. Some researchers speculate that under certain conditions, a galaxy's dark matter halo might behave like a cosmic superfluid, its quantum properties stabilizing the spiral against external chaos. It's a stretch, but not impossible. Superfluids on Earth already defy classical physics, flowing without friction or viscosity. If dark matter has similar quirks, it could rewrite how we think galaxies evolve. Of course, linking quantum mechanics to galactic scales isn't straightforward. The decoherence problem looms. Large quantum effects typically vanish in large, warm systems as they interact with their environment. Yet alternatives exist. Theories like pilot wave dynamics suggest quantum behavior might persist in ways we don't yet understand. Others propose that the early universe's extreme conditions imprinted quantum fluctuations on galactic seeds, leaving relics like this spiral as cosmic fossils of a quantum epoch. Whether these ideas hold water remains to be seen. But that's the beauty of this galactic rebel. It forces us to venture beyond textbook physics, to ask questions we wouldn't dare pose about ordinary galaxies. In doing so, it reminds us that the universe rarely fits neatly into our categories. Sometimes the answers we seek aren't just hidden in the stars, but in the strange, shimmering space between the very small and the unimaginably vast. Space is anything but calm. Imagine a hurricane that never ends, where the winds are made of charged particles racing near light speed, and the rain is lethal radiation. This is the environment our impossible spiral calls home, a region of the cosmos where interstellar weather should have long ago shredded its delicate structure. Yet against all odds, it remains untouched, its spiral arms pristine. To understand how, we need to unpack the forces battering it and the invisible shields that might be holding them at bay. First, the cosmic winds. The galaxy cluster this spiral inhabits is crisscrossed with high-speed gas streams, leftovers from ancient collisions and supernova explosions. These winds carry enough energy to strip galaxies of their star-forming gas, leaving them barren. Most spirals in such environments show signs of weathering, ragged edges, distorted arms, or gas tails stretching behind them like comet trails. But our rebel shows none of this. One theory suggests its dark matter halo acts like a gravitational windshield, diverting the worst of these particle gusts around it. Another possibility lies in magnetic fields. Recent observations reveal this galaxy's fields are unusually well organized, threading through its arms in coherent patterns. These could be acting like cosmic power lines, channeling incoming winds away from vulnerable gas clouds. Then there's the radiation. Young, massive stars flood space with ultraviolet light, while supermassive black holes pump out X-rays, both capable of ionizing gas and shutting down star formation. Yet this galaxy's star-making factories hum along undisturbed. The secret might be in its chemistry. Spectroscopy shows its gas is laced with trace metals, elements that act like cosmic sunscreen by absorbing harmful radiation before it can disrupt molecular clouds. Even more intriguing are the galaxy's dust lanes, dark, dense ribbons weaving through its arms. These aren't just cosmic clutter. They're shields, blocking radiation from reaching star-forming regions while allowing just enough energy through to trigger controlled collapses. The wild card is turbulence. In most clusters, gas churns like a boiling pot, its random motions preventing the orderly rotations needed to sustain spiral arms. But here, the chaos seems tamed. Radio observations hint at shock fronts, vast, structured waves moving through the galaxy's gas, possibly generated by nearby mergers. Counterintuitively, these shocks might be organizing the turbulence, like a conductor turning orchestra noise into symphony. Some simulations even suggest the galaxy's own star formation is part of the solution, with supernova pumping energy back into the gas in precise bursts that counteract external disruption. What emerges isn't just a galaxy surviving the storm, it's one that's learned to dance in the rain. Every destructive force out there seems matched by some internal mechanism, a cosmic balancing act we're only beginning to decode. And that's the real revelation here. Stability isn't about avoiding the chaos. It's about finding a way to move with it. Why does a galaxy 12 billion light-years away matter to us, sitting here on our tiny blue dot? Because this cosmic rebel isn't just a curiosity, it's a mirror. Every time we unravel one of its mysteries, we're glimpsing a piece of our own origin story. The atoms in our bodies, the iron in our blood, the calcium in our bones, all of it was forged in the hearts of stars, scattered across the cosmos by explosions just like the ones that shaped this impossible spiral. When we study its defiance of cosmic rules, we're not just observing distant starlight. We're reading the autobiography of the universe, and by extension, our own. Think of it like archaeology, but on a galactic scale. Just as a single fossil can rewrite human history, this galaxy challenges the timeline of how we thought structures formed after the Big Bang. If spirals could emerge this early, this perfectly, what else have we gotten wrong about the universe's childhood? The answers could reshape everything from how galaxies mature to why certain ingredients for life, carbon, oxygen, silicon, exist in the abundances they do. Without those elements, Earth wouldn't exist. Without galaxies like this one, those elements might never have been scattered across the cosmos in the first place. Then there's the deeper existential pull. For centuries, humans have looked up and wondered, are we alone? Is the universe inherently hospitable to order, or is Earth's stability a fluke? This spiral suggests pockets of harmony can emerge even in the most chaotic environments, that beauty isn't an accident but a possibility woven into the fabric of reality. If a galaxy can dance through time against all odds, what does that say about the resilience of life itself? We're not just passive observers of the cosmos, we're products of its stubborn, creative persistence. But perhaps the most profound connection is this: the galaxy's defiance mirrors humanity's own restless curiosity. It exists outside the expected bounds, just as our species constantly pushes past limits, sending probes beyond our solar system, decoding quantum realms, daring to ask questions that have no answers yet. In a way, the spiral's journey mirrors our own. Both are outliers, both refuse to conform, and both hint that the universe might be far stranger, far richer than we've dared to imagine. So when we point telescopes at this distant enigma, we're doing more than science. We're continuing a conversation that began when the first humans looked up and wondered about the lights in the sky. Every mystery it reveals isn't just a data point. It's a reminder that we're part of something vast, ancient, and endlessly surprising. And that's why this galaxy, impossibly distant, feels oddly close. It's not just a subject of study, it's a kindred spirit in the dark. From backyard stargazers to Hollywood screenwriters, this impossible spiral has ignited a fire in the public imagination, unlike any celestial discovery in recent memory. Amateur astronomers first spotted it in grainy online telescope images, dismissing it as a glitch, until professional observatories confirmed its existence. Overnight, forums lit up with theories ranging from plausible astrophysics to wild speculation, proving that some cosmic mysteries refuse to be confined to academic journals. Science fiction authors seized on its defiance of cosmic rules, weaving tales of ancient alien engineers and time-bending anomalies. One best-selling novel imagined it as a celestial archive, a library carved in starlight by a vanished civilization, its spiral arms encoding secrets meant to outlast the heat death of the universe. The galaxy's haunting symmetry even influenced visual artists. Digital creators began rendering it in mesmerizing loops, its spiral arms flowing like liquid light across social media feeds. A viral art installation last year projected its likeness across an entire city block, with visitors walking through swirling nebulae as if stepping inside the galaxy itself. Meanwhile, filmmakers borrowed its aesthetic for blockbuster space operas, using its impossible structure as shorthand for advanced alien technology. Its influence quietly permeated pop culture, appearing in everything from album covers to high-fashion runway designs inspired by cosmic rebellion. But perhaps its deepest impact has been philosophical. Online communities dedicated to existential questions latched onto the galaxy as a metaphor proof that outliers can thrive against impossible odds, that beauty persists in chaos. Memes juxtaposing its image with phrases like "still spinning despite everything" became digital rallying cries for resilience. Educators used it to spark classroom debates about scientific humility, showing how even our best models can't yet explain this cosmic exception. The most unexpected tribute came from the music world. A contemporary composer created an orchestral piece, translating the galaxy's radio silence into minimalist arrangements, long stretches of near void punctuated by sudden stellar crescendos. Critics called it the sound of defiance, a sonic representation of light surviving against the darkness. Meanwhile, amateur astronomers organized global, spiral watch parties, coordinating telescope observations across continents as if bearing witness to a cosmic miracle. What makes this cultural moment remarkable isn't just the galaxy's scientific enigma, but how it's bridged the gap between academia and everyday wonder. In an age of fleeting digital trends, a single distant galaxy has reminded millions to look up not just with telescopes, but with imagination. It's become more than an astronomical oddity. It's a canvas for our collective curiosity, proving that some mysteries don't just belong to science. They belong to anyone who's ever stared at the night sky and dared to ask, what if? Unraveling the secrets of this cosmic rebel doesn't come cheap. Peering 12 billion light-years into the past demands more than curiosity. It requires some of the most advanced technology ever built, funded by a mix of government agencies, private institutions, and even citizen scientists. The Hubble Space Telescope, which first spotted the galaxy's impossible spiral, costs roughly $10 million a year just to operate. Its successor, the James Webb Space Telescope, topped $10 billion to develop and launch. And that's before accounting for the supercomputers crunching the simulations, the teams of astronomers analyzing the data, or the countless hours of observation time on radio telescopes scattered across the globe. Solving this mystery isn't just a scientific challenge, it's a financial one. So who foots the bill? The lion's share comes from taxpayer-funded space agencies like NASA, the European Space Agency, and their international partners. These organizations pour billions into cosmic exploration, not just for knowledge's sake, but because the technologies developed along the way. From advanced imaging sensors to AI-driven data analysis often spin off into everyday applications. The same algorithms used to model galaxy formation might later optimize traffic flow in cities or improve medical imaging. But public funding has limits, especially when economic downturns shift priorities. That's where private players step in. Philanthropic foundations and billionaire-backed initiatives have become increasingly vital, with figures like Elon Musk's SpaceX and the late Paul Allen's funding for radio telescopes filling gaps left by strained budgets. Even corporate sponsorships play a role. Tech giants like Google and IBM contribute computing power for large-scale cosmic simulations, treating it as both R&D and PR. Then there's the unsung hero of modern astronomy, crowdfunding. Platforms like Kickstarter and Patreon have funded everything from asteroid tracking projects to public data archives. When professional astronomers couldn't secure telescope time to monitor the spiral's radio silence, amateur networks pooled resources to rent hours on smaller arrays. It's a reminder that cosmic discovery isn't just for elites. Anyone with an internet connection can help chip away at the universe's greatest mysteries. The economics of this search reveal something profound. Every dollar spent on studying this galaxy is a bet, a wager that understanding the cosmos' outliers will ultimately teach us more about the rules governing everything else. Whether it's a government allocating millions or a student donating $10, the investment isn't just in one spiral story. It's in rewriting the textbooks for generations to come. The debate over whether we should explore distant galaxies while Earth faces pressing crises is as old as spaceflight itself. Critics argue that the billions spent on telescopes and probes could feed the hungry, cure diseases, or combat climate change, problems that feel immediate and tangible. Yet this view overlooks how intertwined cosmic exploration is with human survival. Consider the technology behind weather satellites, originally developed for space missions, now predicting hurricanes and saving countless lives. Or the medical imaging devices born from NASA need to diagnose astronauts remotely, now detecting tumors in hospitals worldwide. The tools we create to study spiraling galaxies often spin off into solutions for spiraling crises here at home. But the argument runs deeper than practical spin-offs. Studying galaxies like this impossible spiral is fundamentally about understanding our place in the universe, a question that has driven human progress for millennia. When early civilizations mapped the stars to navigate oceans or plant crops, they weren't just solving practical problems, they were seeking patterns in chaos. Today's astrophysicists follow the same impulse, chasing mysteries that redefine what's possible. The discovery of dark matter didn't just explain galactic rotation, it hinted at an invisible framework underpinning reality itself. Who's to say what breakthroughs might emerge from unraveling why this spiral defies the rules? Then there's the long view perspective. Climate change, pandemics, and resource shortages aren't just Earth problems. They're rehearsal for humanity's greatest challenge, becoming a multiplanetary species. By studying how galaxies form and endure, we're essentially reading the universe's playbook on sustainability. This ancient spiral has survived cosmic storms for 12 billion years. Its secrets might hold clues to making civilizations last. The very act of peering across cosmic distances trains us to think beyond quarterly reports and election cycles, fostering the kind of long-term stewardship our planet desperately needs. Of course, balance is crucial. No one suggests launching telescopes while ignoring famines, but history shows that curiosity-driven science often yields unexpected dividends. The microchip, the internet, even the humble GPS in your phone, all emerged from research that seemed abstract at the time. When we invest in fundamental exploration, we're not just buying data about distant stars, we're investing in the kind of creative problem-solving that tackles earthbound challenges too. The same innovative spirit required to decode an impossible galaxy could unlock fusion energy or carbon capture technologies. Ultimately, the choice isn't between Earth and the cosmos. It's about recognizing that humanity thrives when we simultaneously address immediate needs and nurture visionary exploration. This spiral galaxy, with its defiance of cosmic norms, reminds us that survival isn't just about reacting to crises, it's about adapting, innovating, and sometimes, like this galactic rebel, rewriting the rules altogether. The Nancy Grace Roman Space Telescope isn't just another eye in the sky. It's a cosmic detective designed to solve mysteries like our impossible spiral. Slated for launch in the mid-2020s, Roman's wide-field infrared vision will peer deeper into the early universe than Hubble ever could, capturing the faintest whispers of light from galaxies that defy explanation. Unlike telescopes that zoom in on tiny patches of sky, Roman will sweep vast cosmic landscapes, stitching together panoramic views that could reveal dozens more of these enigmatic spirals. If this galaxy is a cosmic rebel, Roman's mission is to find its brethren, and in doing so, rewrite the rules of galactic evolution. But Roman won't be working alone. The European Space Agency's Euclid telescope, already scanning the heavens, specializes in mapping dark matter's invisible web. By tracing how light bends around galaxies, Euclid could finally reveal whether our spiral's pristine arms are cradled by an unusual dark matter halo, or if something even stranger is at play. Meanwhile, the Vera C. Rubin Observatory's decade-long legacy survey of space and time will act as a cosmic motion picture, tracking subtle changes in the spiral's rotation and structure over years. If those arms are being reinforced by hidden forces, Rubin's time-lapse view might catch them in the act, the real game changer combining these datasets. Imagine Roman spotting a distant spiral, Euclid mapping its dark matter scaffolding, and Rubin chronicling its slow cosmic dance, all while the James Webb Space Telescope dissects its chemistry. This multi-telescope approach isn't just about more data. It's about seeing the galaxy through multiple lenses, literally and figuratively. One theory suggests upcoming spectrographs might even detect quantum imprints, subtle fingerprints left by hypothetical actions or other dark matter particles woven into the galaxy's light. Then there's the wild card, gravitational wave detectors like LISA. While designed to sense ripples in space-time from colliding black holes, they might indirectly reveal whether our spiral's quiet core hides a binary black hole system. The absence of waves could be just as telling, ruling out certain merger scenarios that might explain its formation. What makes this era unique isn't just the technology, it's the questions we're finally equipped to ask. Previous generations could only wonder why this spiral exists. We're on the verge of answering how, and in doing so, uncovering universes within the universe we never knew were there. The greatest revelation might not be about this single galaxy at all, but about how many others like it have been hiding in plain sight, waiting for tools sharp enough to reveal their secrets. This impossible spiral isn't just rewriting textbooks, it's igniting young minds in classrooms and living rooms around the world. Take the Galaxy Explorers initiative, where middle school students analyze real telescope data from this cosmic rebel, hunting for clues about its mysterious origins. One 14-year-old from Texas spotted an unusual gas filament in publicly available images, a detail professional astronomers had overlooked, proving that curiosity knows no age limit. Programs like these turn abstract science into hands-on detective work, showing kids that groundbreaking discoveries aren't just for experts in lab coats, they're within reach of anyone with a computer and a question. Universities are leveraging the galaxy's allure too. At MIT, astrophysics students use it as a case study in problem-based learning, grappling with the same puzzles that stump seasoned researchers. How does it retain its shape? Why is its black hole so quiet? These aren't hypothetical exercises, they're training future scientists to think beyond established models, preparing them for a universe full of surprises. Meanwhile, science communicators have transformed the spiral into a storytelling powerhouse. The YouTube channel, Cosmic Mysteries, dedicated an entire season to its enigmas, blending animations with interviews from leading astronomers and racking up millions of views from teens who might have never cracked open an astronomy textbook. The galaxy's greatest educational gift might be its defiance of expectations. When 7th graders in a Berlin classroom built a model of it using recycled materials, their teacher reported a revelatory moment. They kept asking, "But why isn't it falling apart?" That question, that refusal to accept just because, is the heart of scientific thinking. Museums have seized on this spirit too. The Griffith Observatory's newest exhibit lets visitors steer a virtual version of the spiral through a simulated galaxy cluster, feeling firsthand the gravitational forces it somehow withstands. It's one thing to hear about cosmic resilience, it's another to watch a spiral arm hold firm as a virtual black hole whips past. Beyond formal education, the galaxy has become a cultural touchstone for curiosity. Citizen science platforms like Zooniverse report spikes in participation whenever they feature it in their projects, with volunteers classifying gas patterns or tracking star clusters from their smartphones. Even children's books have adopted the spiral as a metaphor for perseverance, with titles like The Galaxy That Wouldn't Quit topping science-themed storytime lists. Perhaps most powerfully, this cosmic oddity is reshaping how we teach failure. When Arizona State University redesigned its astronomy curriculum, they included the spiral's story to emphasize that unanswered questions aren't dead ends, they're launch pads. Showing students how professionals grapple with the unknown demystifies science, explains Dr. Elena Rodriguez, who led the initiative. It's not about memorizing facts, it's about learning to ask better questions. That lesson transcends astronomy, nurturing a generation unafraid to probe gaps in climate science, medicine, or AI ethics. The spiral's ultimate classroom might be the internet itself. TikTok creators have spun its mysteries into viral, solve this challenges, while amateur astronomers live stream their attempts to spot it with backyard telescopes. In an era where algorithms often divide us, this 12-billion-year-old enigma has become something rare, a shared puzzle that invites everyone to the table, from Nobel laureates to fifth-grade stargazers. And that's the real magic, not just that it teaches science, but that it reminds us science is for everyone. The spiral galaxy's hypnotic symmetry has always been more than data points and spectral lines, it's a muse. When digital artist Leela Chen first saw its Hubble portrait, she didn't reach for a telescope manual. She grabbed her stylus. Her resulting piece, Whirlpool of Time, layers the galaxy's spiral arms with translucent brushstrokes of gold and cobalt, each curve echoing the delicate filigree of Renaissance clockwork. It felt like painting a cosmic ballet, she explains. Every star a dancer, every gas cloud a pirouette frozen in starlight. The piece went viral, spawning a wave of fan art that reimagined the galaxy as everything from a colossal Nautilus shell to a divine fingerprint pressed into the fabric of space. Music composers have been equally captivated. When the Berlin Philharmonic commissioned a piece inspired by celestial wonders, experimental musician Ryuichi Sakamoto eschewed the usual crashing crescendos of space music. Instead, his spiral elegy translates the galaxy's radio silence into haunting minimalism. Glass harmonica notes shimmer like distant stars, while a solo cello's sustained tones mirror the slow, inevitable spin of its arms. The effect is unsettlingly beautiful, a sonic paradox that mirrors the galaxy's own defiance of expectations. Meanwhile, underground electronic artists have sampled the actual radio waves detected, or rather, not detected, from the galaxy, weaving its quiet into ambient tracks that pulse with otherworldly tranquility. Poets, too, have found endless metaphor in its resilience. Astrophysicist-turned-poet Jane Hirschfield penned the Spiral Answers, a villanelle that juxtaposes the galaxy's endurance with human fragility. You ask how long a thing so delicate can last. Watch it, 12 billion years and counting. The universe forgets its laws as it forgets its past. The poem spread through literary circles like wildfire, its closing lines etched into the walls of planetariums from Tokyo to Cape Town. Even children's authors have embraced the galaxy's story. The illustrated book The Little Galaxy That Wouldn't Straighten Out turns its stubborn spiral into a parable about embracing one's unique shape in a universe that prizes conformity. The art world's embrace of this cosmic rebel reveals something profound about how humanity processes wonder. When faced with phenomena that defy explanation, we don't just analyze, we create. The galaxy's impossible arms become brushstrokes, its silent radio waves musical rests, its persistence a metaphor for our own. In rendering its mysteries beautiful, artists perform a vital alchemy. They translate cosmic data into emotional resonance, reminding us that the universe isn't just a puzzle to be solved, but a story to be felt. Perhaps the most unexpected tribute came from the world of fashion. Last year's Paris Fashion Week saw designer Iris van Herpen debut a gown whose swirling metallic threads mirrored the galaxy's spiral, its 3D printed filaments catching light like distant stars. Worn by a model suspended mid-air in a zero-gravity simulation, the dress became an instant icon, a fleeting moment where haute couture and astrophysics collided. "It's about tension," Van Herpen told Vogue. "The dress looks fragile, but it holds its shape against invisible forces, just like the galaxy." From Instagram poets to avant-garde composers, this spiral has become a canvas for humanity's collective imagination. Its true legacy might not lie in the papers it inspires, but in the art proof that some truths are best expressed not through equations, but through the quiet ache of a cello's note or the bold stroke of a painter's hand. In the end, science gives us the how, but art dares to ask why. And for this celestial enigma, we need both. Misinformation spreads as quickly as starlight in the void, and this cosmic rebel has attracted its share of myths. Let's separate fact from fiction, starting with the most persistent rumor that the galaxy's perfect spiral is evidence of alien engineering. While it's thrilling to imagine advanced civilizations sculpting stars, the truth is far stranger. No unnatural patterns or artificial signatures appear in its light spectra, and its structure, while baffling, still operates within the known laws of physics. That doesn't make it any less extraordinary. It means the universe itself is capable of crafting wonders beyond our wildest fiction. Another common misconception is that this galaxy exists in total isolation, floating untouched through the cosmos. Early reports sometimes framed it as a lone anomaly, but we now know it's entangled in a web of gravitational relationships. Its survival isn't about escaping chaos, it's about navigating it with impossible precision, like a surfer riding a wave that should have crashed long ago. The surrounding cluster isn't just a threat. It might be the very reason the spiral persists, its neighbors acting as accidental collaborators in this cosmic ballet. Then there's the oversimplification of dark matter's role. Pop science often portrays it as a magical fix-all, an invisible hand steadying the galaxy's spin. But dark matter alone can't explain why this spiral thrives while others in similar environments fray. Current models suggest a delicate interplay of factors: gas dynamics, magnetic fields, even the galaxy's unique star formation rhythm, all working in concert. Dark matter might be the scaffold, but the building stands because of countless subtle forces we're still mapping. Perhaps the most dangerous myth is the assumption that this galaxy upends all of cosmology. It doesn't. Instead, it exposes gaps in our understanding, like a single irregular stitch in an otherwise sturdy tapestry. The laws of physics aren't wrong, they're incomplete. Every anomaly, from Mercury's wobbling orbit to the accelerating expansion of the universe, has led to deeper truths. This spiral isn't a threat to science, it's an invitation to look closer. One persistent speculation suggests the galaxy is younger than we think. Its light somehow distorted to appear ancient. But redshift measurements are unambiguous. This light has traveled 12 billion years to reach us. The real puzzle isn't its age, but how it achieved maturity so quickly, like a child prodigy composing symphonies at 5. Time dilation and relativistic effects have been ruled out. The galaxy's youth is genuine, its early brilliance a challenge to our cosmic timeline. Finally, there's the myth of inevitability, that this spiral's existence means such galaxies must be common. The truth: we've found only a handful of candidates, and none match its perfection. It might be a cosmic fluke, a 1 in a trillion alignment of conditions, or it could be the first of many, hinting at a hidden diversity in the early universe that our telescopes are only now sharp enough to see. Until we peer deeper, its rarity remains part of the mystery, a reminder that the universe reserves the right to surprise us. Dispelling these myths isn't about dimming the galaxy's wonder. It's about sharpening our focus so what's truly extraordinary shines through, because the reality that nature crafted this marvel without breaking its own rules, that we're witnessing a dance of gravity, time, and chance unlike anything predicted, is more thrilling than any fiction. And that's the heart of science, not clinging to old stories, but embracing the unknown with open eyes. Solving this cosmic puzzle isn't the work of a lone genius in a lab. It's a symphony of minds spanning continents, cultures, and disciplines. From the high-altitude deserts where Chile's ALMA telescopes pierce the sky to the supercomputers in Japan crunching galactic simulations, the hunt for answers has blurred borders in ways few other endeavors can. When the first images of this impossible spiral flashed onto screens, it wasn't just one team celebrating. It was a chain reaction of curiosity igniting from Cape Town to Copenhagen. Astronomers in India noticed peculiar gas patterns in the arms, while Canadian theorists ran models suggesting dark matter interactions no one had considered. A grad student in Brazil cross-referenced old radio surveys and found a faint signal others had dismissed. Piece by piece, the galaxy's secrets are being uncovered not in isolation, but through a web of shared data. Late-night Zoom calls across time zones, and preprint papers passed like batons between collaborators who may never meet in person. The tools of this trade are as diverse as the teams wielding them. Europe's Euclid spacecraft maps dark matter's invisible tendrils, while China's 500-meter aperture spherical telescope listens for whispers of hydrogen gas between the stars. American, Russian, and South African researchers debate findings in shared virtual reality observatories, donning headsets to navigate 3D visualizations of the spiral's structure. Even amateur astronomers contribute, like the German schoolteacher whose backyard telescope images helped calibrate light measurements, or the Kenyan coding collective that developed an AI to spot subtle distortions in gravitational lensing data. This isn't just cooperation, it's collective problem-solving at planetary scale. proving that the universe's grandest mysteries can't be unraveled by any single nation or institution. What makes this collaboration extraordinary isn't just the sharing of resources, it's the fusion of perspectives. At a conference in Sydney last year, a Tanzanian astrophysicist pointed out how the spiral's gas flows mirrored fluid dynamics in Lake Victoria's whirlpools, inspiring a new line of hydrodynamic models. Meanwhile, Inuit researchers drew parallels between the galaxy's resilience and Arctic ice formations that stabilize against turbulent seas. These unexpected connections highlight a profound truth. Understanding the cosmos requires more than math and telescopes. It demands cultural wisdom, analogies from Earth's own extremes, and the humility to recognize that brilliance wears countless faces. The data itself flows as freely as starlight. Unlike past eras where discoveries were hoarded for competitive advantage, findings about this galaxy live on open access platforms within hours. A high schooler in Norway can analyze the same Hubble datasets as a Nobel laureate, and a farmer-turned-citizen scientist in Argentina might spot a pattern missed by professionals. This democratization of discovery has accelerated progress exponentially. When one team hits a wall, another across the globe often vaults over it. The galaxy's radio silence, once a baffling dead end, was partly explained when an online forum pooled amateur radio telescope observations dating back decades, revealing subtle fluctuations that professional arrays had overlooked. Yet challenges persist. Language barriers, time zone delays, and funding disparities still strain the ideal of seamless collaboration. Some researchers in developing nations face agonizing choices between joining global projects or addressing local crises, while others struggle with visa hurdles just to attend critical meetings. Even data sharing has limits. Sensitive military satellites occasionally capture astronomical data by accident, but security protocols keep those insights locked away. And when political tensions flare, scientific partnerships can become collateral damage, delaying breakthroughs by years. Still, the trajectory is clear. This galaxy has become a test case for how humanity might tackle even greater cosmic questions, from the nature of dark energy to the search for extraterrestrial life. If we can coordinate across borders to decode a single spiral's defiance of time, what else might we achieve? The answer lies not just in the stars, but in our willingness to look up together, pooling not just data but empathy, creativity, and the shared awe that first made us wonder about the night sky. In a world often fractured by difference, this celestial rebel has quietly become something unexpected. A reminder that curiosity, at its best, builds bridges as enduring as the galaxies themselves.